Okay, so for quadratic functions, we talk about these as second-degree polynomials. And that in the standard form, they're this ax squared plus bx plus c. And in what we're going to call in this course the transformation form is going to be a times x minus h squared plus k. Now, if you look at that very closely, you think, okay, there's our toolkit function of x squared, where we're modifying the horizontal location by subtracting h, and we're modifying the vertical location by adding k, and we're modifying the width of this thing by multiplying that toolkit function by some constant a. And so there's other names for this, but we're going to call it the transformational form because that's what it's going to tell us, is how does this thing transform. And so the thing that really locates a quadratic function is its vertex, right? These are parabolas, either concave up or concave down, now that we have a new term there. And we know the vertex is going to be at h and k, which is what the transformational form tells us. Okay, so let's look at this transformational form, and let's expand this. And let's compare it to this ax squared plus bx. So if I expand it and then collect terms, that middle term, that minus 2ah, those are all constants, right? A is a constant, h is a constant. That's what b equals. And then h squared plus k is my constant c. So let me look at the b one first. B equals negative 2ah, and so we can say h equals minus b over 2a. Now this is a nice handy formula because it tells us then, when we have it in the standard form, it'll tell us where the vertex is, right? Because once we know h, we can get k. So the vertex, if we calculate minus 2a or minus b over 2a and then put that in the function, we'll get the vertex. So k, of course, is f at h. Now this is a little theoretical. I'll have an example on the next chart where you can see how this thing goes very quickly. Normally what you've done in algebra at this point is you're starting to complete the square. Now completing the square I think is a pretty useful thing to do, and I'll review that at the very end. But the very quick way to take something that's in standard form and find the vertex is making use of the fact that h equals minus b over 2a. Okay, so here's the example. I want to find the vertex of this function. Okay, so what I'm going to do, yeah, hang on just a second, okay. And I'll be posting the charts, so if you're missing some details, you can just look at the charts on Moodle. Okay? Mm-hmm. All right, so we're at this point here. So I'm going to calculate h based on this standard form. So I'm going to say, okay, h is negative b over 2a. So I have negative 12 over 2 times 3, which is negative 12 over 6. So negative 2 is my h. And then I'm going to put in that h into my function and evaluate that. And I get negative 16. So there's my k. And so I have my vertex then at negative 2 and negative 16. Now, if you think, okay, here's another formula to remember, this minus b over 2a. You know the quadratic equation, right? Or the quadratic formula. Here, I'll write it on the board here. It's going to be x equals minus b plus or minus b squared minus 4ac over 2a. Now what happens when you get x, those are the two roots, all right? So if you just have an arbitrary parabola, you'll have two roots like this. Now, this turns out to be equally spaced or symmetric with respect to the x location of the vertex. So you have something like this, where the number of units that this is from this axis of symmetry is the same on both sides, and that's what this part is right here, is how far you go to the left, how far you go to the right. So if you just look at this first part of the quadratic equation, you get this minus b over 2a. So if you have this thing ingrained in your mind, this minus b plus or minus the square root of the discriminant, remember that word, over 2a, just look at the very first part. This tells you the value of x for the axis of symmetry, and that's where you're going to find the vertex. So I think, if you just remember where this comes from, think about the quadratic formula, this minus b over 2a is not that difficult to remember. Okay, so now we also have, we know what a is, that's 3. We know what h is -2, and we have k is -16. We can put this in to the transformational form directly once we do this calculation. And so the alternate way to get there is by completing the square. This is much more direct. So notice that a in both of the forms, of the transformational form and of the standard form, that leading coefficient is the same. In this case, it's both 3. Okay, so here's one for you to try. I haven't really given you any questions directly, but let's say we have this parabola here, this x squared plus 2x minus 8. The way you're going to analyze this is you're going to find the vertex, you're going to find the x and y intercepts, and from that you should be able to make a pretty reasonable sketch. So I'll give you a couple minutes to do this. Okay, let's see what we get from this thing then. Okay, so the vertex, we find h, and so that's -2 over 2, -1, and then we can calculate k by plugging in the -1 into the function, and we get a -9. The y-intercept is just going to be -8, right? F at 0 is -8, and so if we factor this thing, we can find the x-intercepts, and so we have the y-intercept as 0, -8, the x-intercepts as 2 and -4, and of course the vertex was -1 and 9. And if I make a graph, I put the vertex in there, and then I have that y-intercept. And then I have the x-intercept on the positive side, that's 2. And then on this side I have the other x-intercept. Now I have something that I call the free point, okay, and free meaning that we get it at no cost or very little cost. If we look at the axis of symmetry, which goes right through the vertex, we know that there's going to be a point that all the points that we find on one side are symmetrical on the other. So if you look at the x-intercept, that thing is at 2, and the axis of symmetry is at -1, so the distance there is 3. So if I go 3 less than -1, I get to -4. You see how that works on both sides? So look at the y-intercept. The y-intercept gives us a free point because we're 1 unit away from the axis of symmetry, and so we have this point here that's going to be at -2 and -8 without any real computation. I just moved it 1 unit to the left of the axis of symmetry, and now I have these 5 points, and I can then sketch my parabola through those 5 points.
I think I misunderstood something you said when you were writing on that board. You were saying that you could use the discriminant to find the x's, but that was definitely not the case.
Well, yeah, you use the determinant to find the x-intercepts, not the determinant, the discriminant, right?
Discriminant.
So you have this numerator that says minus b plus or minus the square root of b squared minus 4ac. So this minus b over 2a is the axis of symmetry, and so then the square root of the discriminant added to that on the numerator gives you one of the values, and you subtract it to get the other values. So it's to the right and to the left of the axis of symmetry. And so you make use of that point to get that, what I call a free point, which is the symmetric point opposite of the y-intercept. Now, I'm going to post, I probably won't go through all this. I'm not going to right now, certainly, because the time is out. But if you want to review how you do the complete the square, those of you that have taken a class from me before where I've taught this, I use this method of writing 2b and then b and b squared and then putting that in. So you can, there's a number of ways to do it. This is the way that I do it. So you'll see this in the notes, and you'll have some opportunity to use this when you're integrating, because changing forms of equations into things that look like these substitution tables will involve completing the square. So it'll be tagged onto here, but it's not really part of this chapter.